presentation. My name is Federico. Sorry, I'm not able to do two things at the same time. Okay, this way. Okay. So I'm with United Nations University, which is not university, so let's say with much more, let's say, consultant for governments, let me say. But I've been working also in the past for 3.5 years as operation manager in compliance teams in Italy, so responsible for setting up system for recycling, take back and recycling electronic waste, portable battery, lead acid value. So I want to share with you some of the experience of particularly that part of my past experience. Just quickly, some of you already have seen those slides, but where do we found nowadays appliances containing POPs, or let's say mercury or POPs, so basically brominated flame retardants? Basically, we find them in those areas. And this is an area where if you want to do a proper recycling, so achieving environmental benefits, you need to add some money, because the intrinsic economic value of those material is not enough. And again, just to give you a rough number, when I was working in Italy a few years ago as operation manager, we were paying 700 euro per ton for proper recycling of energy saving lamps. 700 euro per ton only for the processing, for the recycling. On top of that, we were having more or less the same amount, 700 euro per ton for the transport, because collecting of lamps is difficult, and you can imagine that was and still is the most expensive e-waste streams to deal with from a, let's say, producer organization perspective. Yesterday, a few days ago, we discussed a little bit some of the estimation of quantities of e-waste generated worldwide. I just made some simple calculation before coming here, considering the 2014 data of e-waste generated worldwide, and those assumptions I'm listing here so that if you want you can play with your Colombian number as well. It turned out that we might have worldwide 46 tons of mercury contained in lamps that have been disposed in 2014. 160 tons of PCB, mainly coming from big appliances. Matt already show you where this material can be found. And 1.08 million tons of plastics containing brominated flame retardants. I couldn't make this bubble in scale because otherwise this one was too big. I just made, while Matt was talking, some simple calculation only for Colombia, and it came out 0.28 tons of mercury, which is a lot, I would say, 0.7 ton of PCB only from electronic products, and 6,500 tons of plastics containing brominated flame retardants. This means that we need to get ready from an infrastructure perspective. Time is changing, and product composition is varying over time. We know we have certain regulation, like the ROS directive, that are phasing out hazardous components, but as Matt said, we get rid of something, the mercury, and we have something else, they are saying another in LED, so it's keep us busy, let me say. When we look at rudimental recycling, which is taking place unfortunately in many places, not only in developing countries, sometimes in Europe as well, people just focus on those materials carrying the economic value, copper and others, forgetting the externalities of those hazardous components like mercury or plastic containing brominated flame retardants. And this is why we need to take that into account and sometimes develop a proper strategies. And I think the future, the vision of my personal vision of future recycling, we need to increase the number of materials that are recovered. We need to increase the control over hazardous components, and we need to increase the effectiveness, especially when it comes to some critical materials. I don't want to annoy you too much with these slides, but just to mention, when you process electronic waste, you have a first part where we have the depollution, and then we have the second part when we have the really material recovery. And I think we need to take into account that we have emissions in the first part, and in the second part, the end processing, we have mainly to focus on resource efficiency. But I just want to provide you some slides because on technology, because when we speak about electronic recycling, it's always a matter of finding the best technology to achieve the environmental benefits we want. Control over release of mercury, for instance, is a clear example. And we have many technologies. So I'm a mechanical engineer as a background. I never put a limit to how people can engineer or develop technology. But please keep in mind every technology has some limits, some throughput, some efficiency. And here, for instance, just to make a simple and funny example, if you want to get the copper out of the cables, of course we can use a chopper, so it's basically mechanical process using electricity. A guy developed this technology for Ghana, for Agobloshi. It's a bicycle powder cable separator. So it's again a mechanical process using our own energy. And then I did myself for half a day this kind of activity. So I was using an old technology called fire to get the copper out of the cable. And I can tell you it's quite a heavy job. So I quit that business after a few minutes. So battery. Matt already explained a little bit the classification. This is just a chart I like a lot. You see, you have the different segmentation of batteries. We are focusing today mainly on portable batteries, rechargeable and not rechargeable. As you can see here, you have different chemical composition. So different batteries usually used for different applications. And here is just some trends of the worldwide market of battery. You see the historical evolution, nickel-cadmium using power tools now is declining. You have much more nickel metal hydride, lithium-ion and lithium polymers. And if we go more than 2015, this red and orange is probably even more and more relevant. This is just a breakdown referred to 2013 data. You see how different sectors use portable batteries. You can find a lot of these market study. Again, the main message is keep in mind that all the batteries, even if they are small, might be the same size, are not the same when it comes to chemical composition. In Europe, in the past, before the new battery directive was published, the situation was like this. Some EU member states had technology and collection infrastructure for portable batteries, but they were mainly focusing on those having positive treatment costs, so those that were paid by the recyclers, so mainly lithium-ion and nickel metal hydride, and all the others having high recycling costs. The easier way was landfilling. But then in 2006, the new battery directive came into force. So first of all, policymakers decided to stop or put a limit on the quantity of mercury and cadmium used in new batteries. But this is more important. They said all the batteries need to be collected under the extended producer responsibility principle, and is no longer allowed to dispose them. And we, as Europeans, my previous job as operation manager, we had to ensure a certain amount of battery were collected, and we had quite ambitious targets. 25 up to 45% of the market by 2016, and for small batteries is really a challenge because you need to convince final users not to throw them away. The difference in chemical composition is, let's say, not a major problem, but is certainly affecting the recycling technology we use, because the recycling processes developed for batteries are really dependent on the technology. So usually you have you collect the batteries, but then you need to separate them according to the technology available for their recycling. And this is more or less the usual let's say streams of portable batteries you need to create. So you have usually the non-rechargeable batteries, so alkaline and zinc carbon batteries, the nickel cadmium and nickel metal hydride, lithium-ion, lead acid batteries. I mean, lead acid is of course going with all the lead, and then we have the bottom cells. The separation is mainly done manually. we have in Europe certain companies that developed fancy automatic optical sorting, but I visited some of them. It's funny to see, but when you do some calculation, you realize that the productivity of those sorting lines is not that different to the productivity of few guys doing manual sorting, and the costs are pretty much the same. The main processes for recycling batteries are pyrometallurgical, so furnaces, and Matt already showed some pictures, and in some cases hydrometallurgical processes, so chemical reaction. Here you see, I don't want to go into detail because we can spend hours for every line of this table. You can see for the different battery type, the segmentation we have seen before, the main output or the main targeted material for the recycling technology and the technology. So you see the great majority is still pyrometallurgical, so furnaces. Nowadays in Europe we have more or less 40 companies having engineered processes like this and accepting and recycling those batteries. And you can find the full list of those companies, which are in some cases already accepting material from outside Europe on the website of the European Portable Battery Association. I just to provide you some figures, some numbers coming from, again, my previous job. You see, you have the same batteries segmentation, and here I try to provide you with some ranges of cost. Those costs, or in green revenues, are only referring to recycling. This means that they are not including the logistics, that for small batteries pretty substantial, and also the sorting, which I let already appear this part, more or less can be assumed having an impact of 200 euro per ton. So you see, non-rechargeable battery, alkaline, manganese, zinc, carbon, nickel, cadmium, it's a cost. So for us as a PRO, we have to pay recycler to deliver environmental results. Good job, some material recovered, but the prices of the material recovered could not offset their process cost, so we had to supplement with some money. For nickel metal hydride, lithium and lead acid, we were paid, so this means that the revenues were higher than the technical cost. In the case of nickel metal hydride and lithium ion, recyclers are usually providing offers or paying you on the basis of the actual nickel and cobalt price. That's the main driver in the recycling process. So you see the variation might be really huge. Those are really prices. I mean, I can show you there is a direct link between the price paid and the monthly market value of nickel and cobalt. This is usually the mechanism, how it works. And for lead acid batteries, it's usually linked to the price, London Metal Exchange of cobalt. So again, if you remember the first slide where we had different areas, recycling processes having costs and recycling processes leading to revenues, you see, even all the batteries, they are not equal. So in some cases, if you want the proper recycling taking place, you need to pay as Producer Recycling Association. In some other cases, you can get paid. But on top of that, you always need to add the logistics. So, given also time is up, I will stop here for the batteries. You will get all the slides. You will see there are other information, other slides summarizing a little bit the technical process for other waste streams, e-waste streams, so refrigerators, mixed electronics, lamps, and so on. But I don't want to annoy you too much at this stage because the first focus was on batteries and mercury. So I will stop here, and I'm more than happy anyway if you want later on to know a little bit more detail on technology to speak with you. That's from my end.
Thank you very much, Federico and Martin, for your presentations. So, las preguntas son bienvenidas de parte de ustedes sobre las dos presentaciones que hemos tenido. Vamos a tener una sesión de 15 minutos de preguntas y respuestas.